Hi STAT students, this is the last video of our course. This is finally our Test 4 study guide. I know it took me a while to get it online. I apologize for that. It took me a long time to get the test, so it took a long time to look it over and get you a study guide, but here it is. So there's a blank one on Blackboard under content, under chapters 8 and 9. And then there's also a completed one on there with all of my work. And then of course there's this video where we're gonna work through the whole thing together. So let's talk about the test for a minute. The test only has 19 questions on it. So it's a very short little test. Now, if you notice, the study guide has 40 questions on it. So why in the world are there so many questions on the study guide? Well, your test is going to appear in Blackboard on our page on the side, and I'll send a picture of that in an email to you to kind of show where, but it'll be down at the bottom, like you'll have your content button and your grade book button, and then down here at the bottom, below the Wiley Plus link, down at the very bottom, it'll say Test 4, and you'll click on that and you'll begin your test. And so the way it works is there is a pool of 40 questions that you could possibly be given, and the computer will randomly and automatically choose 19 of those problems for you. And so just to make sure you are completely prepared, regardless of what test you get, we need to be comfortable with all 40 problems. So that's what this study guide does, is it gets you prepared for all 40 problems so that no matter which of the 19 that you get, you are comfortable with them. So let's talk about what you're gonna need for that test. So you are gonna need your T-chart right here. That shows you all of your different T values. That is gonna be very, very important, okay? Randomly looking through here for something else. I'm sorry, it just occurred to me that you need one more item. And of course, there it is. You're going to need your Z table like this, your little chart that has your confidence levels and your Z values. So you're gonna need that. And then of course, it would be great if you had your little handout on hypothesis testing that has your 3 scenarios. So these 3 pages, along with your calculator, are what's going to be necessary for you to complete this study guide and be ready for your test. So make sure you have these either pulled up on different tabs, different screens, or printed out, or whatever works for you. Now, your test 4 will be multiple choice except for the last few problems. These problems toward the back, and I forget how many of these that you could possibly have, but you will have a few problems like this in the back. I believe you could have 3 or 4 like this, where you do have to fill in the blanks, okay? And we'll look at that when we get to the back. Okay, it starts with, those start at number 34, I believe. Nope, 35. So you have 6 of these to practice with, fill in the blank. You are only gonna have 3 or 4 on your test. I think 3, but I can't really remember. So anyway, here we go. We're gonna start and go through them. This is not a multiple choice study guide, even though your test will be until you get to the very end. So this is going to be fill in the blank, the whole thing for us. And then of course your answers are in the back so that you have those. And we're just gonna jump right in and start. Okay, and here we go. It's only over chapters 8 and 9. All right, first question. What happens to the width of a confidence interval as the confidence level increases? And then just as a side note, all other factors remain constant. Okay, well, the confidence level will increase as well. Okay, it will also increase. So the width of the interval will increase as the confidence level increases, which brings us to the next question. How are they related? Okay, well, They are directly related, which means when one increases, the other one increases. Okay, that also means that when one decreases, the other decreases. Okay, so the same thing will happen regardless of which one that you have, the other will follow the same path. Okay, so that's very important that you remember that. All right, next question. When making a confidence interval for the population mean using the T procedures, okay, so remember T procedures would be sigma unknown, okay? The degrees of freedom for the T distribution are, so this wants to know, how do you get the degrees of freedom? Well, remember it's, sample size minus 1. So that's how you get your degrees of freedom. All right, 3 and 4, okay, basically the same question, just a little different there. Wants to know, how do you find this T value? Wants you to give a T value. Okay, let's start with number 3. We have a sample size of 20. All right, well, we need the degrees of freedom. So if our sample size is 20, we need to subtract 1. And our degrees of freedom is 19. Okay, the other thing that we're gonna need is the area. To get your area, you have to use your confidence level. Okay, so your formula for that, for your area, is going to be 0.5 minus your confidence level as a decimal divided by 2. That gives you the area, which is the number up top on your T chart. Okay, so here we go. I'm going to have 0.5 minus, not 98, but 0.98 divided by 2. Remember, you're going to need to put that in parentheses. That's going to give you the area. So let's do that on our calculator together. Okay, I'm going to have 0.5 minus, and then in parentheses, I'm going to do 0.98 divided by 2. That gives me 0.01. That's my area. Okay. Doesn't matter if it's right tail, left tail, it does not matter. You're going to put the T value down and it's going to be positive. Here we go. So here's our T chart. Degrees of freedom is 19. So we're looking at this row. Here are the areas. We said that our area was 0.01, which is right here. We come down our column. There's our T value right there. 2.539. This looks like an old T value from last time. Okay, 2.539. That is my T value. And there you go. Done. All right, let's try this again. Now we want T for a sample size of 25. All right, well, we need degrees of freedom. So 25 minus 1 is 24. So we're going to be on a different row now and a different column. We're now looking at 90% confidence level. So our area is going to be 0.5 minus 0.90 divided by 2. Okay, go to our calculator. 0.5 minus 0.90 divided by 2, you get 0.05. That is your new area. That's our column. Okay, can you see that? Am I too far over? No, you're good. Okay. All right, so we go to our T chart. I go down to row 24. That's our degrees of freedom. I go across. Got too many pencil marks on here. Okay. I'm looking for the area, the column 0.05. Here it is. Come straight down. Here's our T value, 1.711. Oh, I'm on the wrong. No, that's right. 1.711. I just realized I have the wrong answer in the back for this guy. So I'm going to have to make that correction on your study guide. Okay. I think in the back I have 1.729. That's not right. I just copied my answer and it is wrong. We said, let's try that again. Okay. We said that we are degrees of freedom 24. Here it is, 1.711 is what we're looking for. 1.711. So in the back of your answers, wrong answer in the back. I'll tell you what I did is I forgot to change my degrees of freedom to 24. I left them at 19. So this is the correct answer. In the back, it is incorrect. So there you go. Okay, now let's start again. Number 5. How large a sample, so we're looking for N now, should be selected so that the margin of error of estimate of a 95% confidence level for P, so we're dealing with proportions, is this, when the value of the sample proportion obtained from a preliminary sample is this. Okay, so there are 2 formulas for finding sample size. The sample size formula for a proportion looks like this. All right, so let's find out what we have. First of all, the 95% gives us Z. That's where this chart comes in handy. This is for confidence levels. So anytime you have a percentage confidence level, as long as sigma is known or you have a proportion. This is the 2 times you can use this chart. Okay, so 95% confidence level, 1.96 is our Z. Okay, so Z is 1.96. Okay, next thing I need is P hat. P hat means sample proportion. All right, your sample proportion is 0.30, right here. Q hat is not given, but Q hat is 1 minus P hat. So 1 minus 0.30 is 0.70. And then last but not least, we need the error. This is where students mess up. They don't read the problem. They get here and they see a number and it's 0.045 and they see P next to it and they see P is this. And they want to put that in for P. That is not P. Read the words before it. It says the margin of error of estimate for this is this. This is your margin of error. It's hidden in the problem. This is your sample proportion. Your margin of error is this value. And you need to be very careful when you read these problems because with your multiple choice answers, one of the answers will be there if this was used as P. So you need to be really careful. All right, we're going to put this in. We're going to square 1.96. We're going to multiply by 0.3. We're going to multiply by 0.7. Notice those are not squared. And we're going to divide by 0.045 squared. Okay, let's put that in the calculator together just to make sure you're comfortable. I have 1.96 squared times 0.30 times 0.70. I'm going to hit enter. And I'm going to divide by 0.045 squared. There we go. I have 3.98.39. Okay, so N equals 398.39. Now we want a sample size, so we want to round up always. Always, goodness gracious, round up to a whole number. So this is going to round up to a sample size of 399. That's my answer. N is 399. Okay, so this is your formula for a sample size dealing with proportion. All right, Let's look at this one. Okay, Luis is in this one. He wants to create a 99% confidence interval for the mean of a population whose standard deviation is this. Oh, okay, that's new. He wants the margin of error to be 3.1. What sample size is needed? This is a different sample size formula. This one does not include proportion. This one has sigma in it. This is the one you need. There's only two. This for proportion, this for sigma. There is not one for sigma unknown, okay, that we deal with. So we are just looking at these two. Okay, so here we go. 99% confidence interval gives us Z. You're going to need to go to your Z chart. Sigma's known. We're allowed to use it. 99%, we're going to take 2.58. Remember, we take the larger ones with this class. Okay, now we need sigma. Well, it was talking about a population, and then it gave the standard deviation. So this is sigma. This is your population standard deviation. Last but not least, we need the error. Here it is, spelled out very clearly. And now we're just going to plug all the numbers in. 2.58 squared, sigma squared over 3.1 squared. Notice every value in this one is squared. In this formula, P and Q are not squared, so be careful. Okay, if we put that in our calculator, we get 69.82. Again, we always round up, always, and we have a sample size of 70. Okay, so there we go. You may have these 6 on your test, you may not, but there you go. You have them there for you. Okay, let's try another one. We're going to do one more sample size just to make sure you're comfortable, okay, because I want to make sure that you get every possible wording for the problems, okay? How large a sample, so we know we're going to use one of those two equations, should be selected so that the margin of error of the estimate for P is this. Remember, that's the margin of error. And because I see the letter P, I automatically know that I'm looking at this formula. Okay, I have a 99% confidence interval. That gives me Z. Go to my chart, 2.58. Okay, and I have a sample proportion, that's P hat, of 0.68. Okay, now I'm also going to need Q hat, which we know is 1 minus P hat. That's 0.32. All right, we're going to plug it in. So we're going to have Z squared times P hat times Q hat. Again, these are not squared. Divided by E squared. Okay, this is going to give me 2514.64. Remember, you always round up to the whole number. So no matter what this decimal is, it doesn't matter, you're going to round up. And we get 2,515. That's a large sample size. That's okay. That's usually what happens with proportions. Okay, so those deal with sample size. All right, now let's deal with confidence intervals. Okay, we're going to do every possible confidence interval you might run across. All right, first, a random sample of 82 customers, okay, I have an N, who visited a department store, spent an average of $71 at this store. So this sample spent this much. That is your sample mean. That's X bar. Suppose the standard deviation of expenditures at this store is sigma equals 19. All right. We know with confidence intervals, just like with hypothesis tests, you have three situations. You have sigma known, sigma unknown, and proportions. So we have sigma known, okay? Doesn't hurt to label it. There it is, we know it, it's known. And a 98% confidence level. Now for sigma known, we need a Z, okay? So 98%, here's the two situations where you get the Z from this. 98% Z gives us 2.33. There we are. Okay, remember there are 3 steps to a confidence interval. First step is to get the correct and appropriate standard deviation. So when sigma's known, for sigma known, there's step 1. Okay. Next step is we need to get the margin of error. For sigma known, there we go. And last but not least, for sigma known, X bar plus or minus that error. And then this is your confidence interval. So 3 steps. Okay, step 1, and again, this is only for sigma known. We're going to find sigma X bar. We're going to take 19 over the square root of 82. Put that in our calculator, take it out to 4 decimal places. I got 2.0982. Okay, make sure you can do that. Step 2, find my margin of error. I'm going to have Z, which is 2.33, times sigma X bar. That's going to give me a margin of error of 4.89. Okay, and then last but not least, our actual interval is going to be, okay, X bar plus or minus this margin of error. Now, on your test, some of the problems have this as the answer, where they just leave it like that. Some of the problems actually make you find the interval like we always did in class. So just for practice, we're going to make sure that we have both answers because you never know what problem you're going to get. Scan your answers. If they have a plus or minus available, this is the choice. If they don't, if they have a real interval with a smaller and a larger number, you need to keep going. If I take 71 minus 4.89, I get 66.11. If I take 71 plus 4.89, I get 75.89. And that is my answer. So there'll only be one, you won't have both. They're not trying to trick you. It's just that some teachers leave it like this and some leave it like this. So they try to put both options on the test, okay? So you'll see this, either this one or this one. All right, let's try another. The mean IQ score for a sample of 61 students selected from a high school is 87. What's 87? The mean score of a sample. Okay, that's X bar. Suppose the standard deviation of IQs at this school is sigma equals 8.4. Okay, that means sigma is known. We're just doing another one just like this for practice. Okay, we're doing 2 of each for practice. Okay, awesome. So now I see a 99% confidence interval. For sigma known, that means a Z from the chart. 99% is 2.58. Okay, I already wrote my steps up here, so I'm not going to write them again, but step 1 is going to be sigma X bar. So I'm going to have 8.4, that's sigma, divided by the square root of 61. And that, I'm going to take it out 4 decimal places, gives me 1.0755. Okay, step 2, E. That's Z times sigma x bar. This gives me a margin of error of 2.77. All right, last but not least, x bar plus or minus 2.77. You'll scan your answers. If you see that as an answer choice, click it. If you don't, then you need to keep going and do 87 minus 2.77 and 87 plus 2.77. Do each of those in your calculator. You're going to find 84.23 for this one, the subtraction. Down here, you're going to find 89.77 for the addition. And then that would be your answer. Okay, so again, you will not have both. You'll only have one. All right, so these are both sigma known. These are the steps you follow. Get your information, you're good to go. Okay, let's try another kind. A random sample, okay, 1,100 adults, showed that 32% of them are smokers. This is 32% of the sample. Well, anytime you have a percent, you're dealing with proportions. That's the kind we're dealing with. And this is the sample proportion because it came from the sample. That is p hat, and you have to make it a decimal. Divide it by 100. Now, if you have p hat, you're going to also need q hat. So we're going to do 1 minus p hat, and we get 0.68. Based on this sample, the 90% confidence interval for the true proportion of all adults who are smokers is, okay, that 90% confidence level. Okay, there's two types of problems where we go to the chart. Confidence level for sigma known, confidence level for proportion. All right, 90%, we use 1.65. There we go. Okay, let's list our steps for this one. I'm gonna actually scoot this back a little so I can put my steps over there because I don't have a whole lot of room. You know how big I write. Okay, let's put this right here, and then I'll go through and do my steps just like I did. Okay, for proportion, you've got to get your standard deviation of your sample proportion. It's gonna look like this. P hat times Q hat divided by N, and you take the square root. Okay. Second step, you need a margin of error. You're gonna have Z times this standard deviation. Very similar to these steps. Third step, you don't have an X bar, but you do have a P hat. P hat plus or minus margin of error. So very similar to these, okay? Those are your steps. So first step, we're gonna have the standard deviation of the sample proportion. We're gonna have P hat, okay, times Q hat divided by N. All right, we're gonna take that out. I took it out quite a few places actually. That's what I ended up with. Okay, step 2, we need a margin of error. We're gonna have Z times the 0.01406. That's gonna give us a margin of error of 0.023. Last but not least, we want a confidence interval, okay? P hat plus or minus 0.023. That's our margin of error. So again, that may be a choice, or if it's not, then you're gonna do 0.32 minus the margin of error and 0.32 plus the margin of error. Okay, the minus is gonna give you 0.297 and the plus is 0.343. And in that case, that would be your answer. All right. So those are our steps for a proportion. All right. Turn our page here. Let's see what we have. Okay. We have Taika in a grocery store. What's she doing there? All right, let's see what she's up to. Okay. A grocery store is interested in how many customers purchase gallons of milk. Well, Taika randomly selects 300 customers. Okay, she's so friendly. All right. And finds that 230 of them purchase milk. Okay, let's keep going. This is interesting. Use a 95% confidence interval to estimate the true proportion of customers that buy gallons of milk. So this is a proportion problem, okay? But it's set up pretty strange because in order for us to have a proportion problem, we need a p-hat. A p-hat is a decimal, or at the very least, it's a percent that we can turn into a decimal. I don't have either one because this is Z. This is for our confidence interval. A Z of 95% is going to give us 1.96. Your p-hat is hidden in this sentence here with Taika. So she selects 300 customers, that's her sample, 230 of them purchase milk. So you have to create your proportion. You have to take the 230 divided by the 300. When you do that, that gives you a decimal, and that's your p-hat. That one is super tricky. Okay, so we also know our q-hat at that point, which is 0.23. Okay, so that's a tricky one. You may have that. It's not a grocery store. Taika's not there buying milk, but if you end up with a proportion problem that gives you two numbers here, it means you have to create one. Okay, all right, here we go. Our first step, we put our steps on the back page there, didn't we? So our first step for proportion, these little bugs over here. Okay, first step for proportion is S of p-hat. That's going to be p-hat times q-hat over n. Step 2 for a proportion, we need a margin of error, Z times S of p-hat. And last but not least, p-hat plus or minus your margin of error. Okay, step 1, here we go. We want S of p-hat. We're going to have 0.77 times 0.23 all over 300. That's going to give us 0.02430. Okay. All right, step 2. We need a margin of error. We're going to have Z, and I just went right to my chart to get Z. I can go to my chart for proportions. Times S of p-hat. That's going to give me a margin of error of 0.048. And then last but not least, I take my p-hat that I made plus or minus my margin of error. So that may be what you're looking for, or you may need the actual interval. Okay, if you need the actual interval, you're going to get 0.722, comma 0.818. And that would be the answer. Okay, 2 more confidence intervals, and then we'll move on. All right, let's look at this one. We have a random sample of 765 persons. And this sample showed that 13.5% do not have health insurance. Okay, when I see a percent like that, I know we have proportion. So far, we had 2 sigma known, and we will have had 3 proportions. Okay, that's what we've had so far for confidence intervals. So this is p-hat. I'm going to change it to a decimal, divide it by 100. I need Q hat, so I've got to do 1 minus, which is 0.865. Based on this sample, the 95% confidence interval, okay, for the proportion of all persons who do not have health insurance, okay, there's my 95% again, just like the one we had up here. These both have the same Z, they had the same confidence level. Okay, here we go. Very straightforward. We didn't have to create anything like we did up there. S of P hat. All right, we're gonna have 0.135 times 0.865 divided by N, 765. Okay, S of P hat, goodness, 0.01236. Okay. Step 2, we want a margin of error. We're going to have Z times 0.01236, and we get 0.0242. All right, last but not least, we have P hat plus or minus the margin of error. So again, look for that one. If you don't see it, keep going. Actually do the addition and subtraction. Put the smaller number first. You'll get 0.111, comma, 0.519. All right, there we go. This is our last confidence interval, the one we're about to do. This one's the doozy. I don't know if you remember this, but this is where your graphing calculator really comes in handy here, because look at all these nice paragraphs full of information. We have nothing. We have one little set of numbers, and that is all we have here. So we have a sample of 10, okay? That's it. And it tells us to construct a 98% confidence interval. All we have is the sample. This is a sigma unknown. This is the only type of sigma unknown you will have on the test. So if you get this problem, that's your sigma unknown. If you don't, then you don't have a sigma unknown, okay? So here we go. We need a sigma unknown. All right. Well, let's go through and talk about steps for a sigma unknown. For a sigma unknown, we need an S of X bar, which is the sample standard deviation over the square root of N. Well, I don't have a sample standard deviation. All right. Number 2, we need a margin of error. And since we have a sigma unknown, we don't have Z, we have T. Well, I don't have a T, and I cannot use my chart because the chart is only good for these two situations, sigma known and proportion. These are Z's, so I don't have a T either. Then last but not least, I need X bar plus or minus my E. Well, I don't have X bar either. I have nothing. Okay, so now is where we go to our calculator. Okay, so remember what to do. We need to put things in a list. We're going to go to Stat, Edit, L1. Okay, so here we go. I'm going to go to Stat, Edit, L1. Now I'm going to clear this one out because I had already put it in there before. So let's go back. I did Stat. It's already on Edit, L1. I'm going to put my numbers in there. 12, 18, 23, 20, 24, 17, 22, 25, 21, 19. Okay, all 10 numbers went in there. There should be 10. Our sample size is 10. Now we're going to quit. Okay, so now we quit. Quit. Okay. Now we're going to go back to Stat. We're going to scoot over 2 times to calculate, to the calc. Then we're going to go to 1 var stats. Okay, Can you see that over there? 1var stats, that's how we get there. Now, 1var stats is gonna ask for information. All you wanna put in is L1. Everything else is blank. You just put in L1, hit enter, you're done, okay? So, here we go. We're gonna go back to stat. We're gonna scoot over to calc. There's 1var stats. I only want L1. This should be blank. If you have this type with frequency list, this should be blank. If you don't have that type and you have the type that shows up on the screen, all you're gonna put in is L1, everything else, nothing else, okay? And now we have our information. Let's talk about what this means. You get 2 numbers off here. Here's your X bar. We needed that. Let's write that down, okay? I'm gonna put it up here out of the way. X bar is 20.1. Perfect. Okay, the other thing we need is S. Now here's where it gets a little confusing, okay? Because S of X bar is what we're gonna find. We want S. Our calculator gives us S of X. What in the world is that? S of X is the same as S. This S up here, okay? So this is what you want, and we're gonna take it out 4 decimal places. 3.8427, that's the S that you want. So S equals 3.8427. It's gonna say S of X in the calculator, but it's really S. Don't let that confuse you. All right, now we have our information. If we had tried to do that by hand, we would have needed a whole nother piece of paper, okay? So this is what you need to be able to do this problem, should you get it on the test. Okay, so first step, we want S of X bar. Remember, this is not what the calculator gave you. The calculator gave you 3.8427. That's from the calculator, that was S. Divided by square root of n, remember that n is 10. When you put that in your calculator, you should get 1.2152. Okay, now next thing we want is E. We have S of X bar, we do not have T yet. We do not have a T, and we need to find one. Okay, so we need to find T. I'm gonna include that in our step 2. Okay, 2 things needed to find T. We need the degrees of freedom, that's n minus 1, so we have 9 degrees of freedom. The other thing we need is the area. Remember the practice that we did on the first page? That's where this comes into play. We're gonna have 0.5 minus 0.98 divided by 2. Okay, that's gonna give us an area of 0.01. Now we can find T. So we're gonna take our T chart. Here's 9 degrees of freedom. Here's our areas. We found the area to be 0.01. This is our T, 2.821, okay? This has a lot of hidden steps in it. Now we can find E. E is going to be 2.821 times S of X bar, 1.2152. Multiply that together, I get 3.4281. Okay. Last but not least, we actually find the confidence interval. We have X bar, remember that came from 1var stats, plus or minus this E. We only need to go out 3 decimal places. So this could be the answer, or you may actually need an interval. In that case, you end up with 16.67, comma 23.53. And there you go. Okay, So practice these confidence intervals. This is all from chapter 8. You have 2 sigma knowns, you have 3 proportions, and you have 1 sigma unknown. That's what's in the pool, just like what I gave you. You never know what you're gonna get, but you're gonna get some of these. And you at least 3, maybe 4 of these interval problems, true interval problems. So you wanna be comfortable with these, okay? All right, practice this with getting this information here. All right, let's move on to chapter 9 then. That's where number 14 begins, okay? All right, chapter 9. The null hypothesis is a claim about, all right, well, it's going to give you 2 options. It's going to say it's a claim about a statistic, blah, 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 or it's going to say a claim about a parameter, blah, 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 blah. It's a parameter, right? Because it's about a population where the claim is assumed to be true until it is declared false. Now remember, we talked about how that kind of works along with the justice system. We said that a null hypothesis, it's kind of like you're innocent until proven guilty. This is true until you prove it false. Okay, and it's a parameter because it deals with a population. A statistic deals with a sample. That's not what we're doing. All right, number 15. In a hypothesis test, a type 1 error occurs. When does a type 1 error occur? Remember, that's the bad error. That's when a true null is rejected. Okay, it was true, but you rejected it. Remember, that's like what would happen if you had an innocent person went to jail. Okay, type 2 error occurs when you have a false null and it is not rejected. Okay, that's when you have someone guilty who does not go to jail. All right. Okay, number 17, in a hypothesis test, the probability of committing a type 1 error is called what? That is your significance level or your alpha. Okay, that's your significance level or your alpha, but they don't put alpha, they just put significance level. So that's what that is. Okay, in a left-tailed hypothesis test, what's the sign in the alternative hypothesis? Less than, right? Less than left, okay? In a right-tailed hypothesis test, the sign for the alternative, greater than, okay? And number 20, a two-tailed test, not equal to, right? Now 21 is a repeat. I apologize. It's the same as 18, left-tailed, less than. Okay. Let's write null and alternative hypotheses. Okay, Simone. Simone's all grown up. She's got a fabulous job. She's looking for a house. Simone wants to test if the mean price of houses in an area is greater than $145,000. There's your clue. What are the null and the alternative hypotheses? Okay. Your null, and we're just going to use mu, you know, it could be either be mu or p. It's mu for sigma known and unknown. It's p for proportion. We're just going to say mu for now. So your null is always equal to the number, right? It's your alternative. And by the way, I did see it on the test that a couple of questions used HA instead of H1, which is very strange, but there you go. Okay. Shouldn't have put equals, I should have put a colon. All right. If you're testing to see if it's greater than, that's what you put in. Easy enough. Ta-da. Okay. So it should look like this. Here's your null equals. Here's your alternative greater than. It may say HA instead of H1. All right. Sam, okay, has decided he wants to be a successful lawyer. All right. He's trying to move to a new city. He wants to know the annual salary. So he wants to test if the mean annual salary of all lawyers in a city is different than 110,000. Okay, null, and again, you could use mu or p, is equal to that number. Our alternative, regardless of what, either you use H1 or HA, what is different than mean? Not equal to, right? And then HA would be the same thing. Different than is the two-tailed test. Okay, so different than means not equal to. All right, I have to pick on Javi because he's not here for me to do it in person. So I'm going to apologize ahead of time, Javi. Here we go. Javi wants to test if elementary school children spend less than 30 minutes per day on homework because he doesn't do any. I'm sorry, Javi, I couldn't resist. I could have put Kyle Barrett in there too, but I didn't. I put Javi, I'm sorry. Could have been either one of you. All right, what are the null and alternative hypotheses? Okay, so our null is going to be equal to 30. Our alternative, which way you write it, is going to be less than 30. And there we go. Okay, I love you, Javi. I'm sorry. You did blow your tests out of the water. You did a great job on those, so I shouldn't pick on you. Okay, 25. One more like this, just because it's worded a little different. Okay, a calculator company has changed the electronics in its calculators. Previously, the calculator has had a mean lifespan of 6 years. Kyle L, because we have two Kyles, Kyle O, wants to perform a hypothesis test. Okay, he's so curious to determine whether the mean lifespan has changed. What are the null and alternative hypotheses? Well, this one's tricky. The null, of course, is going to be equal to whatever number you see, so equal to 6. What are we going to write about the alternative, though? Because I don't see greater than, I don't see less than, I only see the word changed, okay? Changed means not equal to or different, right? This means this. It's a two-tailed test. So that was tricky. I thought we better go over that. We've never seen one like that before. We've always saw different than or different from, but we haven't seen changed. Okay. All right. Number 26. In a two-tailed hypothesis test with a significance level of 0.025, okay, the p-value is 0.4. Okay, so this is alpha. Our p-value is 0.4. Okay, so two-tailed really doesn't matter. We have that information. What conclusion can be drawn? So based on this, it's asking you, do you reject or do you fail to reject? Okay, well, if you go back and look at any of the pages in the little handout, you will see that if alpha is greater than the p-value, reject. If alpha is less than the p-value, fail to reject. And that's the same for proportions, for sigma known, for sigma unknown. That is the rule, okay? So in this case, alpha is smaller than, okay? And the p-value is larger than. The answer choice you're going to want is that you are going to fail to reject because the p-value is greater than alpha. Because remember, this is the probability. The probability here is greater than the significance level. This is not significant enough to change anything. So we fail to reject. We leave it alone, right? We leave it alone. So this is the answer choice you're going to want in this situation. All right. Okay, in a hypothesis test for a population mean where sigma is known, okay, the test statistic for the sample size of 55 was calculated to be negative 2.14. So that's our test statistic. What in the world is a test statistic? Okay. Well, if you remember, and I tried to talk about this a lot when we were in chapter 9, that sometimes you would hear test statistic, and then on test 4, sure enough, that's all you hear. Okay, test statistic when sigma is known is Z observed. This is your test statistic. The observed value, the one that you have the little formula for, that you have to complete the formula, that's your test statistic. So in this case, it's negative 2.14. Now, because it's negative 2.14, because it's negative, this tells me I have a left-tailed test. Okay, that's what this tells me. All right, find the p-value of this one-tailed hypothesis test. Okay, if you have forgotten how to find a p-value, you take your little packet here, you turn it to sigma known, okay, p-value approach. First thing it wants is Z observed. That's this. This is the test statistic. You already know this. You get to skip step 1. We already know that. Then to find the p-value, you follow this step, okay? We don't have a two-tailed test, so we don't have to worry about the last sentence. But you use Z observed, and you find the area under the curve using normal CDF. If it's a left-tailed test, here's what you put in the calculator. If it's a right-tailed test, this is what you put in the calculator under normal CDF. Okay? So this is a left-tailed test. So if I wanted to, I could draw it. This is my p-value I'm looking for. This is my observed value. Okay, I'm going to go to normal CDF. I'm going to go from negative infinity to negative 2.14, mean of 0, standard deviation of 1. Tells me that right here. Negative infinity, there's my test statistic, 0, 1. Okay, so remember how to find normal CDF? I want this distribution, so I go second bars, normal CDF. There we go. Negative infinity is negative 1 E99. My upper is the test statistic, negative 2.14, 0, 1. There it is if you need it out like that. And 0.016, how far do they go out? 2. My p-value is 0.0162. There we go. Okay, that's how you handle that. All right, number 28. The t distribution is used to perform a hypothesis test when do we use t? When sigma is unknown. What does sigma stand for? Population standard deviation. When we don't know that, that's when we use it. Okay? All right, number 29. In a test of hypothesis for a population mean where sigma is unknown, okay, so we know what page to turn to. The test statistic for the sample size of 64 was calculated to be 3.257. Okay, remember, test statistic there. Now, that's your observed value. When sigma's unknown, my test statistic is T observed. Okay, so my T observed, that's my test statistic, is 3.257. Now that's positive. What kind of test do you think we have? A right-tailed test. Find the p-value. Same thing we did in 27, except sigma was known here. Now sigma's unknown. Okay, if you want to draw it out like this, you can. Except that it's not going to help you a whole lot because you're going to have to go to the t-chart. You cannot use normal CDF on sigma unknown. You only use normal CDF when sigma is known and with proportions. So, p-value approach. We already know T observed. Check. Oh, find degrees of freedom. Okay, we need that. If n is 64, my degrees of freedom are 63. Using degrees of freedom, find the correct row on the t-chart. Okay, now locate the two t values that your T observed falls between. Then go up the two columns and find the two area values. Remember, p-value for sigma unknown is a range. Remember that. We don't have a two-tailed test, so we don't have to worry about that. Okay, so we have a range here. All right, we have degrees of freedom, and then there is our p-value. Okay, so degrees of freedom is 63. You got to turn your page over for that one. Here he is. There's our row. Okay. Now remember, I went ahead and I labeled a cross on the back there. All right. Now my test statistic is 3.257. So the numbers get larger as you move to the right. Okay. 3.257 is actually bigger than this one. So it's way out here on this side. When I go up, what I find is 0.001. Well, I'm supposed to have two values because it's supposed to be in a range. Notice that these area values are getting smaller as your T values are getting larger. Okay, so right next to this would be another column, if there were one, of zeros. So here is my range. My p-value is between 0 and 0.001. Okay, so basically my p-value is less than 0.001. That's the answer you're going to put. P-value is less than 0.001. There you go. This is the only type of sigma unknown p-value problem you have. And this is what it's going to be. So find your T observed, find your degrees of freedom. It's your T value, your observed value is going to be way over here so that when you go up, you don't have two values. You're going to be less than 0.001. That's your p-value. Okay. And we practiced one of those when we were doing hypothesis tests in the sigma unknown part of chapter 9. Okay, next we have Laura. Laura is so friendly. She asked 500 people, that's an N, if they liked the town they lived in. 65% of the responses were affirmative. Means they said, yeah, Laura, we love it. Okay, so this many of the sample means we have p hat. That's our sample proportion. This is a proportion problem, okay? And we have a null hypothesis, okay? This null is only there to give you the p. We don't have an alternative, that's okay. We don't even know what Laura's testing. She's just asking people a question. All right, so compute the value of the test statistic z. This means find z observed. That's what that means. So I'm going to go to my packet for proportions. Okay. Here's Z observed. Remember, this is your test statistic. All right, let's see if we have everything we need. Our test statistic wants P hat, we have that, minus P, that's why they gave us the null, divided by sigma P hat. Oh, that comes from here. This is what we need to find. Okay, so first step, we need sigma P hat. That's going to be P times Q over N, square root. Then we're going to find Z observed. That's our test statistic. That's P hat minus P over sigma P hat. Okay. All right, we have everything we need except Q. It doesn't say Q hat. This is where students get confused. Chapter 8 likes Q hat. Chapter 9 wants Q. So make sure you know the difference. If it's a confidence interval, Q hat. So it's 1 minus P hat. If it's a hypothesis test, it's plain old Q, 1 minus P. So don't get those two confused, okay? Look at your formula carefully. So my Q is 1 minus P, which is 0.4. Okay, here we go. Sigma P hat is P times Q over N. We get a sigma P hat of 0.0219. Okay, number 2, Z observed. Z observed is P hat minus P divided by sigma P hat, 0.0219. Okay, let's put that on our calculator just to make sure everyone's good. 0.65 minus 0.60. Do not hit divided by at this point. Your calculator will get messed up. You can put this in parentheses and divide by sigma P hat. Otherwise, hit enter first, then divide. Otherwise, order of operations is going to mess you up. Okay, Z observed is 2.283. That is my answer. Okay, there we go. All right, we're moving right along. 10 more. We can do it. We're almost there. Okay, Elizabeth. What are you doing, Elizabeth? Okay, Elizabeth claims that less than 40% of Americans, this is supposed to be an S, are allergic to penicillin. Okay, and a random sample of 200 adults, 35% indicate this allergy. Okay, well, since that 35% came out of the sample, that is the sample proportion. That's P hat. Okay, which means this is the actual claim. This is your HO, this is your null. Okay, and since we're doing proportions, that is your P. Okay, that's your P. Calculate the test statistic Z for the population proportion. So again, we're on proportion. We're doing just what we did before. This formula. First, we have to find our standard deviation. Okay, so we're going to need Q. Q is going to be 0.6. Okay, so we're going to find sigma P hat, which is going to be P times Q divided by N. That gives me 0.0346. Then we're going to find our test statistic, that's Z observed, which is going to be P hat minus P divided by sigma P hat. And we end up with negative 1.44. So we'll never know if Elizabeth was right or wrong. We just have our test statistic. That's it. Okay. Now we're going to Disney World. Disney World claims that more than, look at all these errors I'm finding. That one should have stayed, huh? Well, we'll get rid of both these. That more than 22% of park visitors return that same year. So that's our claim. That's our P. Okay, means we need a Q, 1 minus P. All right, this would be our null. Maya, okay, Maya found that in a sample of 175 park visitors, 30% returned that same year. Okay, that's our P hat. When she was asking those 175 people, that's where that one came from. Find the p-value using a right-tailed test. Okay, p-value using a right-tailed test. Okay, here we go. Proportions, p-value. So we're up here. First thing we need to do, we need a test statistic. We need z observed. Then we'll find our p-value. Okay. All right. So we first need to find sigma p hat, just like we did up here. We're going to have p times q divided by n. This gives us a sigma p hat of 0.0313. I don't know why, but I went out 1.4. I went out really far on this. Okay, that was a weird sigma. There. Okay, now we want z observed. We're going to have p hat minus p divided by this sigma p hat. Now, this is a funny little situation because depending on how far you go out with this sigma p hat, if you stop at 1, you're going to get one answer. If you go out to 1.4, you're going to get a completely different answer. So depending on how far out you took your p hat, you might get 2.55 for z observed, or you might get 2.56 for z observed. So I put both answers just in case, okay? All right, here we go. This is a right-tailed test, which means we're over here. Whatever value you want to use, that's what this value is, okay? So how do you find your p-value for a right-tailed test? Normal CDF. If it's a right-tailed test, this is what you put in. Z observed, positive infinity, 0, 1. And that makes sense. Z observed, positive infinity. So we're going to normal CDF. Now, if you use 2.55 or 2.56, it's going to give you a different answer either way. So I'm going to give you both. When you put that in your calculator, if you use 2.55, you're going to get a p-value of 0.00539. If you use 2.56, you're going to get a p-value of 0.00523. It's a pretty significant difference there. Yours will be really clear on the test. This was just a bad example that I made up and ended up with two very different answers. So both of those would be acceptable. And I'm going to go back and I'm going to check your test and make sure that there isn't anything wonky that happened, you know, and you weren't graded weird. So I'll go back and check that question, but there you go. Okay, 33. Test the claim. All right, we have to do an actual test here. Look at there. I used a HA just to kind of get you in the habit of seeing it sometimes in case they use it. Test the claim that for all the population of alligators in Florida, the mean weight is mu equals 550 pounds. Sample data collected by a very brave team of Jonathan and Josh, wow, they risked their life for you guys, shows that n equals 50, x bar equals 525. I did this because that's how it appears on the test. And S is 23.2. When I see an S, what do I have? Sigma unknown. Okay, that's the sample standard deviation. That's what Jonathan and Josh calculated from their alligator data. Here's your significance level. Here are your null and alternative. What kind of test am I looking at here? This is a two-tail, isn't it? That's a two-tail test based on that info. Okay, here we go. We're ready to go. We want to determine the test statistic. I'm yawning, I'm sorry guys, and state your conclusion. Now, it doesn't tell us whether to use the critical value approach or the p-value approach. I'm going to use the critical value approach because that's what you're going to be required to do for most of the problems on the test, unless it specifically asks for a p-value. And that way we can practice more. So I'm going to use critical value. You could use either way. Okay, so I'm going to go to sigma unknown, critical value approach. Here we go, down here. First step, find t observed. That's my first step. So I'm going to go here and then here. Okay. All right. First step, I'm going to have S of x bar, which is S divided by square root of n. That gives me an S of x bar of 3.281. Okay. Then I'm going to use that to get my test statistic. That's what one of the things it wanted. Okay, which is z observed. That's going to be x bar minus mu, comes from your null, divided by S of x bar. My test statistic ends up being negative 7.620. That is my test statistic. Okay, all right, step 2. Find t critical from the t-chart using alpha, remember that's your significance level, as the area, and using the degrees of freedom. If you have a two-tailed test, and we do, divide alpha by 2 first. Okay, let's look at our test here. We have a two-tailed test, and we're doing a critical value approach. That means we have regions. This is the non-rejection region. We're going to have 2 critical values. Oh, you know what I did? I put z observed. I'm so sorry. This is t observed because we're sigma unknown. Sorry, guys. These are going to be your t criticals. Okay, my alpha is 0.2. Now, I'm going to have to take alpha divided by 2 because there's 2 of these. So 0.2 divided by 2 is going to give me 0.1. That's my alpha. Okay, so I did that. All right, it says to go to the t-chart, my degrees of freedom are going to be 50 minus 1, that's 49. And my alpha is going to be my area, that's the row up at the top, of 0.1. Okay, so I'm going to go to my t-chart. Here we go. Erase this on here from last time. Okay, I'm looking for row 49, that's my degrees of freedom, and I'm looking for an area of 0.1. Here it is. I go down, here's my t value. These are my critical values, t critical, 1.299. Now, I need 2. The positive is 1.299, that's from the chart. Guess what the negative is? Negative 1.299. Okay, that was from the chart. Now, okay, so those are my critical values. Okay, step 3, okay, check and see. Is t observed in a rejection region or a non-rejection region? Well, I'll tell you what, t observed is negative 7.620. He's way on down here in rejectionville, right? He's way down here. So he is in a rejection region. So what's my conclusion? Reject the null, reject HO, okay? So it wanted the test statistic and to state the conclusion. That's your conclusion. And we did the critical value approach. We just followed the steps right out of the packet. This gave us our critical values. Okay, last one before we really start getting into those fill in the blanks. Remember, so far everything has been multiple choice, right? Okay, here we go. Kyle Barrett claims that more than 60% of Americans watch sports on the weekends. All right, that's a proportion. Javi doesn't really trust him, so decides to test this. And he asked a random sample of 500 Americans this question. Okay, so that's his Javi sample. Of the 500, 350 responded yes. Okay, so remember what happens? We had a problem like this already. If you have, I think it was Taika and her milk, if you have a sample and a number that responded to the sample and you're dealing with proportions, that is your p hat. You have to come up with the decimal on your own. You have to divide it and you get 0.70. This 60% is the original claim. That's like your null, that's your p. Okay, you're gonna need a q also, which would be 1 minus, which is 0.40. All right, calculate the test statistic z. That's all you gotta do. Okay, we're dealing with proportions. So I go to my proportion page. All I want is the test statistic, that's it. I don't have to go through all of these and make a conclusion. So I'm gonna find sigma p hat and plug it right in. Okay, sigma p hat is p times q divided by n. And I get that is not what I get. Sorry guys, I was looking at the next part. And I get 0.02191. Okay, now I'm gonna find z observed. Remember, that's my test statistic. Okay, that's gonna be p hat minus p over sigma p hat. Now, a lot of students during the test normally come up to me and say, how do I know which one is p and how do I know which one is p hat? Remember, p is the claim, right? It's the claim. It's the original mu or p equals. P hat comes from the sample. All right, it's the percentage from the sample or the number from the sample. Okay, this ends up being that 4.56 that I tried to write earlier. That is your z observed or your test statistic. Okay, all right. Okay, guys, we have 6 left. These are the big 6 hypothesis tests that I was talking about with you. This is where it becomes fill in the blank. These are the only problems, these last 6, where you are actually going to have to type in a number rather than click an answer choice, okay? And you're going to have 3, possibly 4, and you're going to have 3, there's 3 parts to each one, okay? And you do get partial credit, so it's not like you missed the whole thing if you put the wrong one. So I put the problem, and then these are the directions that are going to accompany every single one of these 6. So let's go through the directions first so we're comfortable with these, okay? So first direction, make sure a decimal begins with a 0. I didn't get any decimal answers for any of mine, but I have different problems. You know, yours are just, similar. But if you do end up needing to put in a decimal, make sure there's a 0 first. Don't start with the point. Make sure you start with 0 point something, okay? If you have a two-tailed test, then you're gonna have 2 critical values. Here's how it wants you to type them. It wants you to type them just like this, the -1 first, then this little guy, this is an ampersand. It wants you, it's right above the number 7 on your keyboard. So hold down Shift 7 to get this little guy. It wants this little guy in there. And then the positive version. If you have z values, what kind of z values would you have? That's sigma known, and that's proportion. 2 decimal places. T values, that's sigma unknown, 3 decimal places. And again, I'm gonna go back and check and just make sure that you know, you didn't get marked wrong for something silly like this, but it would really help me if you guys would get it right from the get-go. Okay, then the very last line is going to say the result. All right, here's your possible phrases: reject or fail to reject. Do not put the null. Do not put the hypothesis. Do not put the claim. You're simply writing reject or fail to reject. Those are your choices. That's it. Okay, do not put the word null in there. Okay, so with every single one of these, it is a hypothesis test using the critical value approach. Critical value approach. Okay, how do you know that? Because it asks for the critical value. So for every one of these, you have 3 answer blanks. The critical value, there's an S there, just in case it's a two-tailed test, you'll have 2. The test statistic, remember this is your observed value. And the result, which is either reject or fail to reject. Okay, let's jump right in. All right, so a company that manufactures ceiling fans claims that the fans last an average of 5,500 hours. That claim, ladies and gentlemen, is your null. Okay. Elizabeth wants to test the hypothesis that the mean life of the fans is less than. Okay, so Elizabeth's test is less than. That's your alternative. Now, it doesn't ask for that. You're not going to put that in anywhere. The reason you have this is to know what kind of test you have. And what kind of test do we have? Left tail. Okay. A sample of 48 fans gave a mean life of 5,200 hours with a standard deviation of 100. So this standard deviation came from the sample. That means it's S. This is a sigma unknown problem. How did I know that? Because it gave me a sample standard deviation. It was in the sentence with the sample. A significance level, that's your alpha, is 2.5%. Divide that by 100 and get a decimal. And the distribution for the population is known to be normally distributed. Remember, that's just a little disclaimer in there. Okay, here we go. We're going to take our packet. We're going to turn to sigma unknown, and we're doing critical value approach every time for these last 6. Okay. First step, find T observed. So I'm going to find S of X bar and then T observed. That's step 1. S of X bar is S over square root of N. That gives me, oh, I'm not on the right page. Okay. That gives me 14.4338. Then I'm going to find, not T, sorry, not Z, T observed. This is my test statistic. T observed is going to be X bar minus mu divided by S of X bar. That gives me a T observed of negative 20.785. That goes right here. Notice I went out 3 decimal places because it's a T value. It's a sigma unknown value, okay? All right, step 2. Find T critical from the T chart using alpha as the area and using the degrees of freedom. We don't have a two-tailed test. We don't have to worry about that. Okay, here we go. We said we had a left-tailed test. Here's my non-rejection region. I'm going to have 1 T critical value right there. This is alpha, 0.025. Okay, so My degrees of freedom are n minus 1. My area is alpha. And I do not have to divide it by 2 because there's only one area. Okay, I go to my t-chart. It said T was 47, right? I'm sorry, degrees of freedom was 47. It said my area was 0.025. Here's my T value, 2.012. 2.012. Okay, now here's my question to you. Does that look right? Should you have a positive value on that left-tailed test? No. You got to make him negative. Why do you make him negative? Because it's a left-tailed test. Make sure you do that because otherwise it'll mark you wrong for the whole critical value, part right here. So this is a negative since left-tailed test. I hope I didn't say two-tailed test. I meant left-tailed test. Okay, now, step 3, check T observed. What area is T observed in? If this is what we have, and this is my T observed, is negative 20.78 in the rejection region or the non? Definitely rejection, right? Definitely rejection. So T observed is in rejection region. So what is your result? Reject. It's all you're allowed to write. Reject. Okay, perfect. Okay, well, let's try another one. Okay, number 36. All right, well, we said Sam was going to be a lawyer, but he went back to school now and he became a doctor. So now we're talking about Dr. Malier. Okay, Dr. Malier asks a patient to check his heart rate every day. Well, that's vague. Dr. Malier does not ask a patient to check Dr. Malier's heartbeat. Dr. Malier asks the patient to check the patient's heart rate. Okay, the patient has 20 readings. All right, that's the sample. With an average, that's an X bar of 85 beats per minute. That's BPM, beats per minute. Dr. Malier says that 5 years ago, the heart rate was 81. Okay, we'll move on. Given a 2.5% significance level, that's our alpha, and the fact that all people similar to the patient have a 7 beats per minute standard deviation. What kind of standard deviation is that? A sample or a proportion? That's our population. That's a population standard deviation. That's sigma. So sigma is known here. How do I know that? Because all people, that means a population, and sigma is a population standard deviation. Is there a reason to believe that the heart rate is different than it was 5 years ago? So if we go back to that sentence with the 5 years ago, this is the claim. Dr. Malier wants to test if it's really different. Okay, so it was 81 beats per minute. Dr. Malier wants to know if it's different. That is a two-tailed test. That's not equal to. So this number 5, this 5 years ago, students want to use every number they see. Do we need 5 anywhere? No, it's not part of your problem. It's extra information, just extra, okay? All right, so this is the claim. This is the test. You're testing to see if it's different. That means two-tailed test. Okay, same directions. These directions are going to follow every one of these. I wanted you to get comfortable with them so you don't spend a lot of time trying to read them. You're going to have 2 hours to do your 19 problems. All right, here we go. We have a two-tailed test. So how many critical values are we going to have? We're going to have 2, right? We're going to have a negative and a positive. Here's our non-rejection region. This is alpha divided by 2 because we have 2 of the alphas. So I have to take 0.025 divided by 2 in this case, and I get 0.0125 for each. All right, so sigma's known. I go to my sigma is known, critical value approach. All of these at the end are critical value approaches. Okay, step 1, test statistic, Z observed. Step 2, inverse norm using alpha. Divide by 2 first. We already did that. Number 3, check the region. Okay, so our first step is to find sigma x bar. That's going to be sigma divided by the square root of n. So that is 7 divided by square root of 20. That gives me 1.5652. I'm back to my z's. This is my test statistic, my z observed. That's going to be x bar minus mu, that's from my null, divided by sigma x bar. And I get a test statistic of 2.56. And because that's a z value, I'm only going to 2 decimal places. That is my test statistic. There we go. Okay, step 2, remember you have this nice little chart, this nice little breakdown to follow along with. Okay, step 2 is to find z critical. And I'm going to have 2 of these, right? Z critical, I use inverse norm. I'm going to use alpha. Now I had to divide him by 2 because I have 2 of these. So 0.0125, comma 0, comma 1. Okay, here we go. Let's make sure we remember how to find inverse norm. Second, distribution. There's inverse norm. And my area is on inverse norm is going to be 0.0125. 1. There it is, negative 2.24. Now remember, I need 2 of these. So what's the positive one going to be? Positive 2.24. Those are my 2 z criticals. Now remember, if your test has 2 critical values, you have to type it like this. So we're going to have negative 2.24. Then you're going to have shift 7. You're going to have that weird little ampersand thing. And then a positive 2.24. Okay, put a space in there. All right, step 3, check your z observed. Put your test statistic and see where it falls. Here we go. Where does 2.56 fall? Right about in here, right? That's in a rejection region. So what am I going to write as my result? Reject. And there we go. Okay. All right, let's try another one. Okay, so far we have only done, let's see, we have done 2 of those. We had a sigma unknown and a sigma known. Okay, let's see what Maya's up to here. She's done with Disney World. Okay, now she's taking polls at school. All right, Maya claims that more than 12% of the students in her school do not have reliable internet access at home. To test this claim, she sampled 300 students. 22% of the students in her sample, that's p hat, make it a decimal, this is a proportion problem, okay? The significance level for the hypothesis test is 1.5%. Divide that by 100, okay? All right, we are almost set. We need a null and we need an alternative, okay? We're dealing with proportions, so we don't have mu anymore, we have p. This is always going to be equal, so we're going to set the null equal to 0.12. Maya is going to test and see if it's greater than 0.12. That's what the more than would mean. What kind of test is greater than? Right tail. Okay. We have ourselves a right tail test. We're going to have one critical value. It's going to be positive. Here's our non-rejection region. Here's our alpha. We don't have to divide it because there's only one. All right. And we're going to jump right in. So we go to this little handy dandy packet. We flip over to proportions, critical value approach, calculate your test statistic or Z observed, find Z critical with inverse norm, use alpha as your area. We don't have to divide it first because it's not a two-tailed, and then check your region. Okay, so first part, we need sigma p hat. All right, we have P, it's 0.12. We also need Q. Okay, Q is going to be 0.88, 1 minus 0.12. So sigma p hat is P times Q over N. Sigma p hat gives you 0.01876. We will get our test statistic, that's our Z observed. Oops. Okay, that's going to be p hat minus p divided by 0.01876. That gives us a Z observed of 5.33. And remember, for my Z's, I only need 2 decimal places. Make sure you put these answers in the right place too. Don't put that on that top line with critical value. Okay, number 2, we want to find Z critical. All right, we're going to do inverse norm. We're going to have our alpha, comma 0, comma 1. Okay, let's try that, see what we get. We're going to clear that one out. Okay, inverse norm, I went second bars. I have 0.01501. Okay, I have negative 2.17. Let's see if that makes sense. Does it make sense to have a negative 2.17 as our critical value for a right-tailed test? No. It's a positive 2.17. You are going to have to make sure this is positive because it's a right-tailed test. That's extremely important. Okay, it's little things like this that'll mean the difference in your grade. All right, number 3, we're going to look at Z observed. And where does this fall? 5.33, way on down here. That's going to be that Z observed is in a rejection region. So what is your result? Reject. There you go, reject. Okay, moving right along, we have 3 more. So we did sigma known, sigma unknown, and proportion. Well, guess what? We're going to do each one of those one more time because depending on which of these problems you get, we want to make sure you're comfortable. Same directions. See what we have here. This one has so much extra information that it confuses students every year. Every year. You do not need all these numbers. So we are going to have to try to figure out what is extra and what is actual problem information. Okay, here we go. On a stretch of highway where a posted speed limit is 75 miles per hour, data collected 5 years ago indicate that the average speed of vehicles was actually 73 miles per hour. All right, I don't know what's important and what is not. We're going to keep going and we'll come back and dig through that. Luis and Laura recently found that a sample of 35 vehicles were traveling an average speed, that's X bar, of 76 miles per hour. They would like to know whether the average speed of vehicles is now different from 73 miles per hour. Okay, now we're getting somewhere. It is known that the population standard deviation, that's sigma, is equal to 5. So sigma is known for this problem. The significance level is 1%. Don't forget to divide that by 100. It's 0.01. Okay, so here we go. We know we're dealing with mu, okay? Here's the sentence that makes the first one make sense. So Laura and Luis want to know whether the average speed of vehicles is now different. That's a not equal to. That's a two-tailed test. Different from 73. That means your null is equal to 73. That means when you go back up to this first sentence where it says this is the posted speed limit, we don't care what the speed limit is. Data collected 5 years ago, we don't care. The average speed of vehicles, that's what we care about. That is the mu, okay? So be really careful if you end up with this problem about speeding cars. Luis and Laura won't be in it, but that beginning information there is not part of the problem. You really have to, weed through this and find what it wants. So sigma known, critical value approach. Here are your directions. Don't forget, this is going to be Z observed, okay? Now for a two-tailed test, remember, you have two critical values, a positive and a negative. You also have alpha split into two pieces, so we have to divide him. 0.01 divided by 2 is 0.005. Okay, here we go. So you can go back to your packet. You can go to sigma's known. Here's your 3 steps. Test statistic. Z critical is inverse norm. We've already divided alpha by 2. See where Z observed falls. Okay. First step, sigma x bar. That's going to be sigma over square root of n. That's 0.8452. Z observed, that's our test statistic, is equal to x bar minus mu, and that comes right from your null, divided by 0.8452, sigma x bar. Z observed ends up being 3.55. Remember, you only go out 2 places for these unless it's sigma unknown, and then you have to go out 3 because it's a t-value. Okay, step 2, we need Z criticals. We're going to do inverse norm. Our area, we already divided it by 2, is 0.005, comma 0, comma 1. We put that in our calculator. We get negative 2.58. Now remember, we need the other one. We need the positive version. So we want both. When you go to put these in, you have to put the negative one first. Space, then you're going to hit that shift 7. It's going to give you that little ampersand thing, right? And positive 2.58. Okay. Then your result of the test, we take Z observed, 3.55, and here it is about here. He is in a rejection region. So what are you going to type? Reject. And there you go. Okay. So notice that both of our sigma known problems have been two-tailed tests. Hint, hint. Good thing to think about. Okay. All right. Well, here's Taika and Simone. Let's see what they're up to. They're always doing something. Okay. They should have a TV show. All right. Taika and Simone, tested the life of 40 batteries. Wow, well, right out of the gate, we have a sample. Found them to last an average, we have a sample mean, of 1,500 hours with a standard deviation. Oh, we have a sample standard deviation of 100 hours. Look at there. All the information was in the sentence with the sample. So we are sigma unknown. Critical value approach. Okay, the company claims they last 1,600 hours. All right, well, that's the claim. Okay, using a significance level of 5%, that's our alpha, 0.05. Do the ladies have enough evidence to claim these batteries have a shorter lifespan than the manufacturer claims they do? What are we going to put in for shorter? That is a less than. And less than means left tail test. Okay, here's another hint. Notice that both of our sigma unknowns have been left-tailed tests. Okay, another little hint there. All right, here we go. We're going to have left-tailed test, one critical value. There's our alpha, non-rejection region. Okay, test statistic is our Z observed. All right, we're ready to go. Okay, so now we're going to have, okay, we'll go to sigma unknown, critical value approach. We're going to do T observed, that's our test statistic. T criticals from the chart, we'll go to the chart in a minute. And then we're going to check and see if it's in the, T observed is in the rejection region. So first step, S of X bar. We have S divided by square root of 40. That gives us 15.8114. Ooh, that's a big S of X bar. Okay, then we're going to do T observed. That is our test stat. I put Z observed. Sorry guys, this was T observed. Okay, since they're T values, we want 3 decimal places. Okay, we're going to have X bar minus mu, 1,600, over 15.8114. We get a T observed of negative 6.325. Okay, so remember that's the test statistic and we went out 3 decimal places because it's a T. Okay, step 2 says we have to go to the T chart to find T critical. Degrees of freedom is going to be 40 minus 1, so 39. Our area is going to be alpha, and we don't have to do anything to it because there's just the 1. So our T critical, and by the way, is it going to be positive or negative? It's a left-tailed test. You better make it negative, right? All right, here we go. Degrees of freedom, 39. We're way up here at the top, row 39. Okay, and our alpha was 0.05. Here's our T critical, 1.685. But remember, we are going to make it negative. Why are we making it negative? Because it is a left tail test. Okay, negative 1.685, 3 decimal places for a T. All right, last step. Where does T observed fall? Here we go. Negative 6.325 is a negative value. That is in the rejection region. So the result is reject. Reject. Okay. Oh, last problem. All right. Very last problem. Let's see what Kyle Lowe has been up to. Did you know that Kyle L. He loves animals. Okay. He finds out that only 20% of his community is interested in building a new animal shelter. He asks 300 citizens, that's your sample, whether they are for or against the new shelter. He finds that 30% of the citizens are interested in building the shelter. Okay, let's stop right there for a minute. Now, this says 30 and then it has a percent in words. You know why that is? They're trying to trick you into thinking that P hat is 30 because they think you're not going to read. They think you're going to pull the number out. Well, P hat is your sample proportion. He cannot be a whole number. Do not fall for it. This is 30%. Divide by 100 and put 0.30. Really careful on this, okay? He uses a 2%, 0.02, significance level. Can he safely conclude that the actual number of people interested in building the shelter is higher than 20%? Now, I don't know if you caught it or not, but we already knew we were dealing with 20% right here. They're counting on the fact that you are going to be lazy and not read the problem. So they didn't write a number. They wrote it out in words. It's right there in front of you. This is a proportion, so we're talking about P. P equals 0.20 is your null. Your alternative is P greater than 0.20. Make sure this problem is super tricky that you read the whole thing. And then as a greater than, this is a right tail test. So let's go over this again. Hint, hint. Your sigma knowns are two-tailed tests. Your sigma unknowns are left-tailed tests. Your proportions are right-tailed tests. Just a little way for you to verify that you're going in the right direction there, okay? So this is a proportion problem. Same examples, or directions, I mean, okay? Here we go. This is going to be Z observed. Okay, so if we take our handy dandy packet, we turn it over to proportions. There we go. We're going to follow the steps for the critical value approach. Okay. First step of the critical value approach, we need Z observed. Okay, so we need the test statistic. We're going to have sigma P hat equals P times Q. Well, what's my Q going to be? 1 times P. 1 minus P, 0.80. Ooh, it's been a long day. Okay, divide by N, take the square root. You should end up with 0.02309, okay? Now we're gonna find our test statistic. There it is. We're gonna do, sorry guys, P hat, 0.30, minus P, 0.20, divided by sigma P hat, and I came up with 4.33. Remember, that is your test statistic. Do not put it up in critical value area. Okay, number 2. Now we need Z critical. There's only going to be one, right? I didn't draw a picture. We're going to be greater than, that's your right-tailed test. Here's our alpha. We're going to have one Z critical. Is that Z critical going to be positive or negative, guys? Positive. Better be positive for a right-tailed test. Okay, we're going to do inverse norm, 0.02, that's our alpha, comma 0, comma 1. That's going to give you negative 2.05. We just said not okay. You're going to make it positive because it's a right-tailed test. It's a greater than test. Make sure you do that before you put it in the blank. All right, last but not least, our Z observed is 4.33. Where does that fall? Z observed is in your rejection region. Now, we are going to reject. We have unfortunately rejected all 6 of these tests. Are you going to be rejecting all of yours? I don't know. I didn't look to see. So that could be a really unfortunate coincidence, or it might be the same. I really don't know. But, you know, I made these numbers up to reflect the type of problems that you are going to have. So just be really careful. Don't assume that you're going to reject them all. Okay. But here are your answers. Remember that number 4 is actually wrong for your answer. Number 4 is 1.711. So you want to make that correction there. Okay. All right. Well, study the study guide. Make sure you can do these problems. We did the whole 40 problems in just over 2 hours. You're only going to have 19 problems, but you also only have 2 hours. So we want to make sure you get through it all. Again, don't panic. I'm going to go back and check your tests and make sure that you didn't get marked off for something silly, but be careful. And I will talk to you very, very soon. I hope you're staying healthy. I will send you an email next week talking about that test and when it will be open and where to find it and all that good stuff. But until then, have a good weekend and stay healthy, and I miss you bunches. Bye-bye.